Hello, this is Mr. Huff, and I real quickly want to talk about precision in the context of this engineering class. So we're going to start at the end of this presentation because that is the most important place to go. You can find this in Unit 5 on mypltw.org. So we're looking at precision. The first idea is that it's just an estimate. Precision is an estimate. So if you take a measurement with a ruler or with a dial caliper, you are estimating that last digit. Remember when we used the dial calipers, we rounded to either a 0, a 3, a 5, or a 7 that we were going to estimate that last number to be. And if you're using a ruler, you measure like the halfway between like the 16th measurements. You can estimate the 32nd of an inch using a regular ruler. It's an estimate, it's not an exact value. If your measurements are estimated, that means your calculations are also estimates because they are built on the measurements. So that means that everything is an estimate as far as we're concerned. That makes science and engineering is a little bit different than a math class. Math, you get one specific answer, and in engineering, you need to keep in mind that your values, your answers are estimates of what the actual value is. The other idea is that you can't be, your certainty of a measurement or a calculated value is tied to the lowest precision number that you used to get there. This is the idea of significant figures. So if you have a measurement, two measurements, one is 2 inches and the other one is 3 7/8 inches, the 3 7/8 is more precise. But if you use those two to find an area, you can't tell me any lower than 1 inch because your first measurement was 2 inches and that's a whole number. You don't have any fractions identified, so you can't tell me anything more precise than 1 inch. And let's pull these up real quick. So precision of answers, here are the main ideas. If I specify a precision, then that's what you have to do. So like if I said, like in the Puzzle Cube project, we wanted 4 decimal places, that is a specified precision. And I'll have some more of that kind of stuff this year. Common sense, we'll talk about in a moment. Accepted conventions, for instance, the precision of money is usually 2 decimal places. We don't say $1 and 0.2743 cents. We talk about $1.27. We don't go any further than 2 decimal places. That is the accepted convention. And then the least precisely measured value we just talked about, and the significant figures determine that. Okay, here's the slide about common sense. Common sense is this. If you have some people that are riding the train and you do this calculation and you say, hey, there should be 9.3 people on this train, are you going to have a 0.3 of a person? So you wouldn't count that. You would just say 9 people, not 9.3. And if you were going to go buy paint by the gallons, if you needed a little more than 4 gallons, you wouldn't buy a half gallon of paint. You can't take a can, cut it in half. You have to buy 5 gallons of paint. That's what it means by common sense. All right, the other thing I want to talk about is problem solving in engineering. There are 4 steps I want you to follow, and I have these written down in my room, but you need to commit these to memory, and I need to give you lots of problems so you get lots of practice. The first thing you're going to do is write down the question, word for word. The reason for this is that if someone were to open your notebook, they need to be able to look at your work and tell exactly what you were doing, and if they have the question in front of them, then they know what you were trying to solve. So documentation in a notebook needs to be very, very complete. The next thing you need to do is include a drawing that supports the question. Everything needs to have a drawing. If it doesn't have something you need to solve the problem, like if we're solving area, if you have the little diagram showing where the parts are so you can calculate area, that's really helpful. But if you're talking about like the bike jump data, you could draw a picture of someone jumping a bicycle off of a ramp, and that would help me understand that you know what the problem is talking about. Step 3 is FSA. This stands for formula, substitution, and answer. So I want to see the formula you're using to solve the problem. Substitution, basically what I want to see is what did you put in your calculator to get the answer? Or what are you going to put in your calculator to get the answer? You replace the formula components with numbers from your problem. And then the last part is answer. So your answer needs to have units with it. If it doesn't have units, it is wrong. There are a few things we look at in engineering that are ratios that don't have units, lucky you, but most of them will. So I need to know if it's inches or meters or newtons or pounds per square inch or whatever. As far as your answers, I want to see 5 important numbers. Think about 5 significant figures, and don't worry about rounding. I don't want you to round at all. Just put down your answer, and I have a couple of examples here. If you look at this, 12.345, that's 5 numbers. 123.45, that would be 5 important numbers. Remember, when you are looking at a problem that has leading zeros, these leading zeros do not count. So your 1, 2, 3, 4, 5 would be everything after the second zero after the decimal. So if you have questions on this, please ask. Next and last and most important thing, skip lines between your problems. I should be able to look across the room and see that you have different problems on your page. Don't cram your work all together. It makes it hard to read for you and for me, and it makes it easy to make mistakes. So that's the last one. So 4 steps: always write the question word for word, draw a picture, FSA, formula, substitution, and answer, and then lastly, skip lines between your work. And that's all I have.